We're going to start today with Professor Dag Nummedal. He's the director of the Colorado Energy Research Institute at the Colorado School of Mines in Golden, Colorado. Dag has been running this institute since its opening day on July 1st, 2004. Previously, he was a professor of geology and geophysics at Louisiana State University and the University of Wyoming. He's served as the manager of E&P Geosciences at the Unocal Corporation in Houston, Texas. Dr. Nummedal's research over the past 30 years has covered coastal and shallow marine sediment dynamics, planetary geology, sequence stratigraphy, and a number of other things that I cannot pronounce. So here's a man who I think has some really strong credentials to talk about global warming, the reality, the fact that it's here, and what we can do about it. Dr. Nummedal?
Thank you, Max. Thank you for putting this symposium together. As a university, we are pretty unique both in the States and globally. The only thing the School of Mines really does is energy, earth, and the environment. And we do that on a very solid foundation of math, physics, and chemistry. So it's a very rigorous technology program, and building or combining that sort of with a focus on energy makes it a very exciting place to be these days. Very exciting for us on the faculty, and also very exciting for the students, as far as we can tell, judging by the very large number of good applicants that we have these days. You want me to talk about global warming, that it's real, and that's easy. It's definitely real. We also know that it is man-made, and the fact that it's man-made is actually a good thing, because we can do something about it. I would be a lot more worried if global warming was an intrinsic characteristic of the sun or something internal to the Earth system that we couldn't control. The fact that it's man-made is the best thing we have going for us. These are the topics, a little bit on the basic physics, on the climate change, and then the trends towards cleaner energy technologies and policy objectives. Now, there are lots of websites out there, of course, that deal with global warming. And it's with websites like with newspapers and tabloids. It all depends on what particular source you go to. So I put on two here, which I found to be very, very reliable, very credible. One is at the site of the American Institute of Physics, The History of Global Warming Discovery. I think you'll find that article. There are lots of articles on there, but they're very precise, they're very well researched. Also from UCAR's website, on the basic principles of atmospheric radiation. I think you'll find both of those websites very, very informative. When you go into the history of global warming, it's kind of fascinating that it started with theory. It started with physics. People in the 1800s, Tyndall in Britain, chemists, Svante Arrhenius in Sweden and others, fully started doing experiments on what happens actually when you send daylight, in other words, energy in the frequency of normal daylight, in through an accumulation of CO2 gases. And that did, in fact, demonstrate, both theoretically and experimentally, that, of course, that CO2 gas is warming up. And that's what this particular diagram shows. This is from one of UCAR's websites. Incident radiation from the sun in the visible wavelength starts stirring up the action amongst the molecules in the atmosphere, and the more CO2 molecules are part of that mix, the more effective that transfer of energy is. With the increased mobility, increased movement, kinetic energy of the gas molecules, of course, then the heat goes up. That's what heat is. More stirring, more action of the molecules in the gas. And this is then being trapped because the radiation that is generated by that molecular action is at a longer wavelength than incident radiation, so it doesn't escape back to space. And that's why it's called sort of greenhouse effect. You're trapping the heat in the atmosphere. The greenhouse effect is not exactly the best term because, as we all know, when you go into a greenhouse, what really has a great deal to do with the fact that it's warmer in a greenhouse than outside is that we have closed doors and closed windows so that you don't get the convection of heat back into the rest of the atmosphere. Nevertheless, it's a reasonably approximation for what's going on in the atmosphere. We talked about the physics and why the globe should warm when we increase CO2. So let's look at the data. Is there in fact evidence that it's warming? Well, certainly. Here are two very famous curves on temperature changes over the last 2,000 years. These kinds of curves are reconstructed by sampling gases in ice, for example, in Greenland, by sampling different kinds of organic material, which can be carbon dated, so we know exactly the age of different materials. And from the isotopic composition of the gases in ice and organic material, you can extract a paleotemperature signal. And when Casper gets here later on, he'll talk much more about the paleoclimatology. So that's the 2,000-year perspective. Now let's look at the current state of affairs. And these are data from the NOAA website, and Peter Tans, also previously at NOAA up in Boulder. And there are three particular graphics here that I think support exactly what the physics argument out of the American Institute of Physics is saying. And that is, you start by adding carbon to the atmosphere. And here's the historical record of global carbon emissions from 1750 till today. Obviously, it's been a pretty straight linear increase in carbon emissions for reasons that we all understand very well. Follow up to that, on a slightly different time scale, is then measurements of CO2 in the terrestrial atmosphere. This is the most famous curve of them all, the so-called Keeling curve, after David Keeling, who started as a postdoc at Scripps Institution of Oceanography in 1956. That was the first international geophysical year. And I was an elementary school student at the time, and I think it was that international geophysical year that turned me on to earth sciences at the time, because there were a number of very exciting questions and results that were asked. Since that time, we've been measuring CO2 concentrations in the terrestrial atmosphere many, many places around the world, and they show essentially the same kind of trend. The ups and downs here are related to the breathing in and the breathing out of the northern hemisphere vegetation on a seasonal basis. So the physics theory, as I showed in the first slide, is well understood. The input of CO2 is documentable. The response in terms of increased CO2, the increase of carbon is documentable. The response in terms of CO2 in the atmosphere is very well documented, and the temperatures are rising. It's a pretty ironclad case. Now let me just take one more slide to put it in the context of sort of a broader geological timescale. So instead of looking 1,000 or 2 years back, let's now go back to about 450,000 years ago. The ice ages. Here are 4 ice ages over the last 450,000 years. During the ice ages, terrestrial or global atmospheric concentration of CO2 was around 180 parts per million. During the interglacial periods, like what we're in now, normal CO2 concentrations were around 280 parts per million. And every 100,000 years they went up and down, because ice sheets have come and gone like clockwork for every 100,000 years for a long, long time. So this is the range that nature has imposed on the planet, a range of about 100 parts per million in variation between glacial and interglacial conditions. Now, where are we today? We're here. And as of January 7th, 2011, last Friday, the global number for atmospheric CO2 stood at 389.69 parts per million. And that's exactly where that star falls on this same diagram. So the message is here that not only are we at a very high concentration of CO2, but we're way beyond. We're essentially doubled the CO2 volume relative to nature's range of natural variations induced. And just not to go into too much detail here, but all of you can appreciate the difference in climate here in Colorado. Getting back to Max Tyler's opening remarks, he was worried about the movement of the pike and the die-off of the aspen forest. Well, during the last ice age, it was pretty cold and icy here in Colorado. We have lots of glacial deposits everywhere. We know so we can see where the glaciers were at that time. So you can easily visualize and think through the difference to the ecosystem of the state of Colorado between an ice age condition and an interglacial one like we have today. And now we have put enough CO2 into the atmosphere to actually double the amount of CO2, double that natural range that oscillated us back and forth between ice ages and interglacials over the last 400,000 years. That's a pretty scary scenario. To summarize this a little bit on the science, CO2 concentrations in the atmosphere are definitely going up. The physics of heat retention is well understood. The world is warming up. there is very little room for scientific debate about the fundamentals. Now, what to do about it, however, that's where we increasingly need to start putting our thoughts and efforts in terms of research. We should have debate, we should have technology development, we should have policy and economic analysis. And hopefully this initiative in the Colorado legislature this year is one of those kickoff events to really start the debate to focus on these issues, moving beyond the climate change itself. I'm fundamentally an optimist, and for that reason I like this little graphics. This is one of these posters that you can buy in a number of souvenir shops and put on your wall. And this one on optimism I thought was very appealing, because it says that the difference between stumbling blocks and stepping stones is how you use them. And the relevance to the climate debate is that a lot of people around us are worried that doing something to mitigate climate change or reduce the growth or the acceleration of climate change is going to be enormously costly and disruptive to the global economic system. Well, that's if you look at these stones as stumbling blocks. If you look at the stones as stepping stones to new and cleaner and potentially much better economic infrastructure in the world's energy system, then that sort of puts the whole thing in a very different light. And I certainly hope that we will choose to build a series of stepping stones towards a new and cleaner energy economy. What we are choosing as a pathway forward to change the global energy system is, first and foremost, the most important thing we can do is to use less energy. And for what we do research-wise is then to deal with efficiency in the terms of building smarter grids, better control systems, more advanced fuel cells, better transmissions and conversion, regardless of the generating source. That's one very big contribution, greater efficiency throughout the energy system. We also do a lot of fundamental research to help increase the penetration of renewable energy. Solar is clearly very important. We are particularly focused on photovoltaics, and the reason we are so strongly focused on solar energy and photovoltaics is that we have our neighbor 2 miles down the street at the National Renewable Energy Lab, which when it was established in the late 1970s was actually the Center for Solar Energy Research. So they have always been a world leader in this, and it's logical for the university next door to focus on similar subjects. We also do quite a bit of work in biofuels, in geothermal and wind energy. And then the third category, which I think is very important, we also do quite a bit to look at how the fossil energy infrastructure can be made cleaner, because it is such an enormously dominant energy infrastructure on the planet. And in fact, it's growing currently. The use of fossil energy is growing faster than the use of renewable energy. So we have to deal with that fossil energy infrastructure. The way we deal with it is to look at fuel shifts from heavier to lighter hydrocarbon molecules, coal to gas, for example. We also deal with carbon capture and storage. Fourthly, we have reactivated our nuclear energy research program. It's one of about 15 nuclear energy research programs in the nation. It's a degree program also, and we're pleased to see how many students are coming into that program from all over the country. So, and students, as an aside here, you know, when you listen to Wall Street people and other economic forecasters, they talk about this concept of leading indicators, leading economic indicators or leading indicators of some kind. My favorite way of thinking about leading indicators are students, specifically looking at what students enroll in. Most young students have a much better perspective of what the future will hold than people do in my age bracket. So by looking at where the students want to major when they come to School of Mines, or they come to University of Colorado, or they come to Colorado State, that's a very good indication of where the future technologies are going to go. And right now, the two most popular programs in terms of attracting the best students from across the world to the School of Mines is photovoltaic energy and nuclear energy. Solar. Why do we focus so much on solar? Well, we like it, and I mentioned we have NREL right next to us, but more importantly, it's not so much what we like. It's not necessarily what I think is a promising technology here for the future, but what a credible body like the National Academy of Engineering thinks. National Academy of Engineering has about 2,000 members of the top engineers in the nation. And sort of when a body like that expresses a view of what are very, very promising future technologies, I take it seriously. And in a recent poll that was made about 2 years ago, the membership of the National Academy of Engineering said that the global challenge number one for the engineering discipline is to make solar energy economical. Right today, solar energy provides less than 1% of the world's total energy, but it has clearly the potential to provide much, much more. In fact, let's look at that potential. It's quite staggering. Current total global energy generation is about 13 terawatts. Terawatts is lots of watts. Now, projected increase by 2050 is an additional new 30 terawatts of energy. So translating that into something we can sort of visualize, to build that many new power plants, if we build them in the form of, say, coal-burning power plants, a big one of which would be 1 gigawatt, or a big nuclear power plant is also 1 gigawatt, to put in 30 new terawatts of generating capacity across the world over the next 30 years, we need to build 666 of these power plants per year. 666 new gigawatt power plants across the world per year. Pretty staggering. In contrast, the sun sends in, totally free, 120,000 terawatts. Free for the taking. And sort of building out another 30, when we have 120,000 terawatts to start with, seems a lot more reasonable if we can find the right technologies to do it effectively and with relatively limited amount of aerial expense of solar capturing, solar panels, etc. The problem, however, is that we can't solve it all by investing just in solar energy, because in the near term, oil and gas demand and probably coal demand will actually grow. This is from the Energy Information Agency. There are several projections, and I'm not going to go into them in detail, but I haven't seen a credible projection from anywhere yet that argues that fossil energy is going to decrease in its role in driving the global economy. So how do we deal with fossil energy? Well, one of the first things is to look at different ways, different kinds of fossil energy, and what their carbon footprint is. And this diagram, which has a lot of details in it, is a compilation of CO2 emissions per unit energy generated by different kinds of fuels. Lignite or low-ranked coal is the worst, about 1,140 tons of CO2 per gigawatt hour of electricity. Regular coal, 800 to 1,000. Natural gas, 360 to 485, quite a bit better, less than half of the worst kinds of coals. And then, of course, the renewable energy systems down here, or sources, have much, much lower carbon footprint. So one thing that we can certainly start by doing is to find effective ways of substituting natural gas for coal. And when you do that, not only do you get the benefit of the lower emissions related to the combustion of natural gas versus coal, but if you look at the overall system, how we use coal in our economy, there is a big, big difference as well. A friend of mine, Bill Daly, out at the Lawrence Livermore lab in California, has put together some of these diagrams, which are now sort of becoming the standard Department of Energy diagrams, looking at how energy flows through our national economy. These are different types of energies being generated: nuclear, hydro, biomass, natural gas, coal, and this is imported fuels. Now, what Bill is trying to show here is that as you go from the generation side of the energy, and as it flows through the economy, how much of that energy is being lost and how much is being turned into useful energy, the kind of stuff that drives the projector here in front of me. And when you look at the coal here, you look at the enormous amount that is being lost relative to the amount that is useful. In contrast, natural gas has a fairly substantial amount that is percentage fraction that is useful. The reason that is so is that there is an enormous amount of energy loss related to the way that we deal with coal in the overall system. We mine it to begin with. It takes an awful lot of energy to operate a mine, to operate a coal mine in particular. Then we put it on trains, and we ship those trains from Wyoming or western Colorado to Houston and New York and places far away. That takes an enormous amount of energy as well. So when you combine the energy losses in the system in the way we use coal currently, compared to the energy loss in natural gas, which flows quite readily through pipeline systems, that's another factor of 2. So depending a little bit on how you put all these numbers together, you can make a very credible argument that that you produce on the order of 4 times as much CO2 per unit energy when you use coal as when you use natural gas. So now, might there still be a future for coal? Well, certainly the Chinese think so, the Indians think so. China is investing enormously in coal research these days. They're way ahead of the US and European countries presently in building new types of coal burning plants with limiting carbon emissions, partly to help alleviate the global warming, but also partly because they believe this is an export technology down the line. Also, there are ways of doing coal processing in situ, in the subsurface, and you keep the SOx and the NOx and the mercury and the ash underground. You bring up a syngas, which you burn, and then in the end, if that syngas, if you capture the CO2 when the syngas is burned, and you store that back underground using a carbon sequestration type technology to capture and store the CO2 underground, then you can actually get a coal energy from coal at a much certainly lower carbon footprint than what we do currently. Here in Colorado, we have established what's called a carbon management center. That is one of these centers that is not specific to School of Mines. It's a center of the Renewable Energy Collaboratory, which this legislature established in 2006. And in that collaboratory, then, the mines portion of the research is to work a lot on geological carbon sequestration. How do we make sure that the CO2 that is injected underground stays there permanently? And that requires that you understand the geology, you have the geophysics tools to image where the CO2 is moving underground and all of those kinds of issues, and there's a lot of research going on in that. The Carbon Management Center also works on terrestrial sequestration, in other words, changing agricultural practices to make the soils contain more CO2 or carbon than they did before. And other terrestrial things too. That's a focus of the Colorado State University. Then we do a lot of work on greenhouse gas accounting systems, looking at some treaty monitoring and verification with the University of Colorado Boulder and evolving partnership with the Los Alamos lab. The reason why I like carbon sequestration is something we can do right now. In fact, we are doing it right now. There's quite a bit of carbon sequestration going on around the world, but it's called enhanced oil recovery. And the reason why enhanced oil recovery is driving this industry currently is that there is no global price on carbon yet. That was the long-term objectives of the Kyoto Treaty. The meeting in Copenhagen tried to get there, we didn't get there. A meeting in Cancun is putting us on a slightly different path, probably a better path, but it's going to be a long while before we have a price on carbon. So there's no economic incentive for large industrial companies to store carbon yet. But there is an enormous economic incentive to store carbon in the form of enhanced oil recovery, and it's a very good first step. Here's a map of North America based on the Regional Carbon Sequestration Partnership that's showing in these reddish colors here all the areas where there is an enormous potential to take CO2, store it underground, produce more oil in the process. And yes, that oil will be burned, and yes, it will emit CO2, but it's American oil, and we stored CO2 to get it, compared to burning the oil that we're bringing in from the Middle East or elsewhere, where they're not storing any CO2 to produce it, and has other security issues tied to it. So using CO2 to enhance American oil production is a very good thing. And right now, there is probably an industry in this country on the order of about $100 billion private industry currently engaged in CO2 enhanced oil recovery in the US. It's already a very large industry. Texas leads among all the US states. The US is way ahead of the rest of the world in terms of really developing this technology the way it should be done. And increasingly other countries are following suit. It's a good step. Problem is that even if we fill up all the reservoirs, oil reservoirs we have in CO2, we only have about 4 years of global CO2 emissions. We have volume, we have room for storing only about 4 years of global CO2 emissions, which is why, in the next slide, the real future for carbon sequestration is to store it in very deep aquifers, 6,000, 7,000, 8,000 feet below the ground, aquifers that are far below the surface, near surface aquifers that we use for groundwater for human consumption. And when we do that, then we have in North America room for about 100 to maybe 300 years of global emissions. That should take us beyond the use of any kind of hydrocarbons in society at all. What our colleagues at Colorado State University are doing is to deal then with terrestrial sequestration, where things like conservation tillage, for example, you don't till, you don't plow in the fall, and all of that helps you build back up CO2, so that over the last 100 years, the way that we have operated over lands in the dry American West in particular, it's been one where we have been releasing CO2, a pretty large amount. But that, to some extent, is a good thing, because the soil now is undersaturated for CO2. So when you put in place the right agricultural policies, you can now capture CO2 and bring it back down into the soil profile. Good for agriculture and a large volume of storage potential. So finally, there's a couple of remarks here on sort of policy. Again, I'm not a policy person, but in the legislature here, I think it's appropriate to at least talk about some of the issues that policy makers will be thinking about. The first one probably gets right to the kind of questions that our representatives are being asked all the time. If we're putting in place policies to limit global warming, is that going to be a ruin or is that going to be a boost to the economy? Well, let's just look at what some previous people have concluded. Nick Stern wrote a very famous report in 2005. It was commissioned by British Prime Minister at the time. And he concluded that there is a net cost, of course, related to, this was specifically for carbon sequestration as a tool. There's a net cost, but vastly less than the cost of doing nothing, which would be flooding, displacement to agricultural zones, spreading of diseases, etc. And that's undoubtedly correct. The McKinsey, the large industrial consulting company, business process consulting company, came with a study in 2008 where they concluded that a shift to a low emissions energy technology will sort of be basically a wash as far as the economics is concerned. There are some cost savings related to energy efficiency and new low emissions technologies, like all our fluorescent light bulbs that we all use these days. But then there are also some net costs, they argue, for processes like carbon capture and sequestration. To me, what I think is more important is to look at the historical evidence, what we have done before. There have been lots of major industrial transitions in world history related to energy. We switched from wood to coal, for example, in the 1750. That's what began the Industrial Revolution. That's what began that curve of CO2 in the atmosphere to rise. But overall, I think that very few of us would argue that we want to go back to the energy system that we had before that switch. So that technology switch from wood to coal clearly was a huge boost to the economy. Churchill switched the British fleet famously from coal to oil during World War I and worked wonders for the speed and efficiency of British warships, but also it's ushered in another major economic boom with an oil-based economy. The high technologies in the 80s and 90s, a major industry transformation. Obviously it costs some to build new computers, etc. But it clearly has been an enormous boost to the economy. So I can't imagine there any reason to believe that a switch to new energy technologies should be any different, but helping induce a major global economic growth. This is the last slide from the National Academies, this particular report that came out. And I put this one in again because hopefully the Colorado legislature will be dealing with the global warming in the rest of the session. What they recommend in terms of sort of policy approaches, they're not making specific policy recommendations, but they feel that the kinds of issues that national and state policies need to address include adopting a mechanism for an economy-wide carbon pricing system. I couldn't agree more. All economists that I talk to say that it's very simple. If you want to have less of something, you increase its price. We want to have less carbon, so increase the price, put the price on it. They also, Academy also argues that they should complement then this carbon price with a portfolio of policies to increase energy efficiency, establish viable carbon capture and storage technology, and new nuclear technologies, which is exactly the recommendations we are following in terms of the research program we are implementing at the School of Mines. And as soon as possible retire or retrofit older greenhouse gas intensive infrastructure. and then also encourage a lot of regional flexibility and policy experimentation. Colorado is already in a leadership position in terms of policy experimentation, and we should continue that. And of course, create new technology by investing heavily in R&D. And I wanted to point that out, that this is not only kind of a self-serving goal that we want more money for research, but it's kind of sad to see the last 30 years of the trend of American investment in energy technology. It has dropped precipitously, far more than the reduction of funding in any other industrial sector. So there's a detailed report by the Brookings Institution in 2010 who shows this. So at a time when new energy technologies are more important than ever, the fact that we have dropped by nearly a factor of 10 the relative amount of federal dollars and private industrial dollars, I should say, not just governmental, but private dollars, that we are investing in energy research has dropped by a factor of 10 over the last 30 years. That's not a healthy situation to find ourselves in. I think we can conclude that the planet is indeed warming up, and we know why. There are viable approaches to limit the magnitude of this change by developing and deploying more efficient solar energy technologies, particularly photovoltaics, and of course other renewables. In parallel, we have to implement a fuel shift from coal to natural gas, and then we have to capture and sequester the CO2 emissions that cannot be avoided. And I think that new energy technologies and the policies that favor their deployments, I view them as stepping stones, not stumbling blocks, but as stepping stones to a growing Colorado economy and a potentially also growing opportunity for American technology exports if we act fast, because lots of other countries see that this is a technology opportunity that they are facing and they want to capture the global market. Thanks for your attention. The question was about, is there a sort of magic number for atmospheric concentration of CO2 above which we will have essentially a runaway type greenhouse effect? No, there isn't a consensus. For the longest time, atmospheric scientists were arguing that if we could keep it below 450 parts per thousand, then maybe we could get by with a global warming average of about 2.5 degrees Celsius. Now, after that, I think at one time they said 500, then it was lowered to 450. Over the last couple of years, several climate scientists have been arguing that no, we actually need to decrease it from where we are today. We need to get lower than the 392, is that what it was, which it was this past Sunday. We need to actually decrease it from where we are now. So there is no consensus. But there's another way of looking at it, and that is that any kind of technologies that we put in place right now to start decreasing the CO2 emissions, even if they're not the most effective in the world, will have more impact in the long run than if we wait till we have some sort of gold-plated technology 30, 40 years into the future. It's an idea of compound interest. You put a little bit of money in the bank every day and it really grows. But here we want to do the opposite. We want to take a little bit of CO2 out of the atmosphere every day, starting today. That will have much greater long-term impact on the global carbon balance than waiting for some of these new technologies. Roughly speaking, the CO2 emissions into the atmosphere fall in 3 categories. One from coal-burning power plants, roughly 1/3. Then all kinds of automobile transportation. And then for the second third, and then everything else. I think that one of the reasons why nuclear is maligned is sort of the perception of the nuclear waste storage. But there are a couple of statistics. The only energy industry in the world that has had, not the world, in the US, the only energy industry in the US that has had no fatalities is the nuclear energy industry. People are killed in coal mines. There are all kinds of other accidents in all other energy industries. There have been no fatalities in the American nuclear energy industry. As for the magnitude of the waste storage, we have been storing waste for 50 years. Nothing has happened yet. That's a pretty good track record. There are clearly future ways, better technologies of dealing with the waste if we can work our way through that political issue. The shift now from Yucca Mountain in Nevada to maybe the waste isolation project in New Mexico opens up a new door. There's a blue ribbon panel that the Nuclear Regulatory Commission appointed about 4 months ago. They're supposed to come out with a report within the next 2 months on a totally new perspective on how we deal with the waste problem. The only thing that concerns me about nuclear is not the waste, it's not the safety, but the proliferation. If you look at the history of nuclear power, the Soviet Union and we were the only two countries that started with a nuclear bomb, and then we developed a nuclear energy industry. All the other 20 or so odd nuclear powers in the world today started with nuclear energy and then sort of evolved into bomb-making capability. So the border between peaceful nuclear energy and weapons making is clearly very, very porous. That's a big concern. And in terms of technology, the newer sort of modular type reactors that people are working with right now, I think will be much more cost effective. We'll get at some of your economics issues. Both you and I are old enough to remember the cost overruns in the 80s, the 70s and 80s, that every nuclear power plant was sort of built like a custom home and was different from all the others, and there were enormous cost overruns all the time. And modern nuclear energy industry with modules are like 100 to 200 megawatts. So a bit more sort of standardized tract house type development project, and hopefully that'll help getting the economics and the cost a little bit better under control. Way out into the future, of course, there are people that are optimistic that nuclear fusion can become a viable industry. There's a big international consortium built around the ITER facility in the south of France, which tries to contain the plasma with electromagnetic fields. So the typical, the fairly traditional way of trying to constrain plasmas. But I think we have another experiment going on in this country which is far more advanced, and that's the National Ignition Facility out at the Livermore National Lab, and my boss is heavily involved, John Poet, a physicist, VP of Research at School of Mines, heavily involved in that project. We talk about it all the time. And this is a way where we try to control a nuclear fusion reaction by having tiny little pellets, sort of the size of a pinhead, and you confine the reactions within these tiny little pellets from the deuterium to tritium transition. And the physics, theoretically, is working splendidly. The experimental facility is expected to be turned on this year. And if that turns out to be possible to control a thermonuclear reaction, then all the other energy problems could just go away over the next several decades. It's a very exciting development in basic physics in terms of new ways of looking at nuclear. I think that the Colorado legislature has already done quite a bit, pushing forward legislation to encourage that shift from coal to natural gas. I think that's a big thing. Looking at legal and financial incentives to look at an integration of natural gas and renewables, using natural gas as a backup for renewables, so that you have a balanced energy infrastructure where the gas will take over when the sun goes down and the wind stops blowing. That kind of hybrid fossil and renewable technology, where the grid itself acts as part of the storage, I think is a very, very important thing to do. And in fact, we're starting to do a little bit of modeling on that. The Colorado Oil and Gas Association is in fact in the process of negotiating a project with NREL and probably with Mines and a few others to start looking at whether we can model what is the right distribution of different energy generating resources to have a balanced renewable fossil energy system.